Okay, we are looking at the Calculus 2 Practice Test 2, this very, very long thing. Oh, no, I gotta make this screen bigger. You're gonna have to wait. Okay, so we're doing this trig integral. We've got a sine and a cosine, which whenever we have this, if both are even, different process. If one of them has an odd degree, we break off the extra odd one, like I did thusly. Break off that extra sign, leaving sine squared, cosine squared. The extra sign is going to be our du. Turn the sine squared into cosine squareds, and we do our integral in terms of u. We get this. Notice that I am doing an indefinite integral here. Really should have here plus c, since that's an indefinite integral. Then convert back to our original, since I did a u sub, before I plug in my limits. Or if I'm going to use limits over here, once I did the u, I need to convert my limits over into u limits, which I was just too lazy, didn't feel like doing it. Convert it back into thetas. So our final answer is 8/15. Another trig integral here, we're doing tangents and secants. If they are both even, if we have even tangents and secants, we use two of our secants to be our du, and we let u be tangent. But if they're both odd, like in this case, we break off a secant tangent. That will be our du. U is secant, du is tangent secant. We convert over to u's, do our integral, and then convert back. So there's our final answer. You can pause that if you want to look through the details. Next page. Basically the same integrals before, really nothing different. The only difference here is we've got an odd cosine, so our du is going to be the extra cosine. So we pick up a negative here. Did I get the right answer? Let me pause this. No, this is good. It was the other one. Here we're good. U is sine, du is cosine. Notice over here, this was important, and I kind of skimmed through it. Since our du was going to be sine, u is cosine, we need another negative, because derivative of cosine is negative sine. Okay, so we get that. That's our answer. This is a trig sub. Anytime we have something that looks like this, x squared plus 9, x squared plus 1, x squared plus something, and we can't just do partial fractions or a direct substitution. If we have to use trig sub, we use tangent. So here x equals 3 tangent theta, square root of 9 is 3. dx then is secant squared. 3 secant squared, that's a 3 right there. And then we do all of our subbing. Make sure you sub in for dx also. And we get all the way down to where we get here. We get a cosine over a sine squared. We had to do a little converting there. We had an extra secant on top, a tangent squared on the bottom. So I had to do a little converting here into sines and cosines. And then that's just a u sub. U is sine, du is cosine. So we get 1 over u squared. We get all the way down to where we're at u's. Now we have to convert back into sines and cosines. Then we have to convert back into x, or excuse me, our final answer should be in terms of x. So we got to be careful here. We draw the triangle. Yeah, I drew the triangle up here because at some point we're going to need sine of theta. It's right there, sine of theta. We knew tangent of theta was x over 3, x over 3, opposite over adjacent. Pythagorean to get the other side. This is our final answer, plus c. Okay, next page out of like 40 pages. Okay, another trig sub. If we have something that looks like a squared minus x squared, we use x is a sine theta. We're going to need to draw a triangle at some point. We do all of our subs, even the dx. That's where these go wrong. Don't forget the dx. Do all of our substitutions. Down here, we get an integral of sine squared. Remember, when you have sine squared or cosine squared, you have to use the half angle formula. For sine squared, that's 1 minus cos of 2 theta over 2. And you're always going to take that and split that into two integrals. Integral of a half minus integral of cosine 2 theta over 2. The 2 and the 4 canceled there. That's where these 2's came from. Do each integral separately. That's a substitution right there. We get an extra 2 in the bottom, which cancels. Then when we get down here, we need to convert back into x's. So theta was arcsine of x. Let's see. Where is my final answer? Oh, so a definite integral, so I had to plug in some limits here. Okay, so right here, theta is arcsine of x over 2. So when I plug in a 2, 2 over 2 is 1. I want arcsine of 1 minus arcsine of 0. And then our other piece, this guy here, sine oh, I couldn't find it. It's in here. Double angle formula. Sine of 2 theta is twice sine theta cosine theta. So I had to do a little algebra here. There's sine of theta, x over 2. Here's cosine theta from the triangle. 2 sine theta cosine theta. So I got this extra 2 that I had to cancel out. And then plug in. Here's our final answer. We get pi. That's our answer. Okay, here we got to use long division. Anytime the degree of the top is bigger than or equal to degree of the bottom, you must use long division. Separate this into 3 separate integrals. Those we can just do. That one's a natural log, and we're done. That's the final answer. Next page. This is a partial fractions problem. It's a rational function. Polynomial on top, 1. Polynomial on the bottom. Do our partial fractions decomposition. We get a is 1/7, b is negative 1/7. Do our separation. Each of those is natural log. That's a natural log absolute value of x there. Another partial fraction. You have to factor the denominator first. It's -2 and +1. And then we do our whole partial fraction game. We find a and b. And then this integral becomes this integral, which is much easier to integrate. That's just a couple natural logs. Okay, this one was much more work. We have to do, because the degree of top and bottom is 3 on top and bottom, we have to simplify the bottom and do the long division. So that's here, and I get this. Oh, that's a typo right there. There's no x there. Negative x plus 3. And then I do the partial fraction decomposition using those denominators. Because this is an irreducible quadratic, I have to have a linear term on top, bx plus c. Looks just like the equation of a line. Then I go through a bunch of work to solve for a, b, and c. And I get a is 1, b is -2, c is 2, which gives me this integral. Always split this piece up into 2 pieces. The bx over this stuff plus the c over this stuff. This one's always going to be just a direct substitution. U is the bottom, du is some multiple of the top. This piece is always going to be an arctan. So there's our final answer. Okay, another trig sub. This is of the form. That's it. Really, 3/2. That's a square root cubed. So this is of the form square root of a squared minus x squared. We use sine equals a, or x equals sine theta. So right there, don't forget your du. And then plug everything in and do all the simplifying. And after all of our canceling and everything, we get antiderivative of tangent squared. I don't remember that one. So I broke that up into secant squared minus 1. I know the antiderivative of secant squared is tangent. I know the antiderivative of 1 is theta. So we get, I'll see there, arctan theta minus theta. Then we got to draw our triangle to figure out what arctan of theta will be. It's not arctan. I'm lying to you there. That's tangent. That is tangent. Which is what I used. It was, I don't know, maybe that was just a stray mark. That's just tangent. Antiderivative of secant squared is tangent. And then tangent of our angle here is opposite over adjacent. Theta from here is arcsine of x over 2. Okay, next one. Degree of the top and bottom are the same. So we could do long division, but here's a trick we can use on these linear ones. I want to split this up into two fractions, add and subtract when I need to make this piece equal to 1. So just separating this top, this over this is 1, 25 over that stuff is this, and then it's just antiderive. Take the integral, plug in our limits, we get this guy. Yet another partial fraction. You got to factor the bottom. Bottom's bigger. We don't have to do long division. In fact, you can't. Like long division won't get you anywhere. Here are the coefficients you should get. If you followed my scheme, A's here, B's here. This is your final answer. Okay, this is the trapezoid rule problem. Our delta x here is 1, b minus a, 6 minus 0 over 6. So we're going every 1. Trapezoid rule says to do, just use this formula here. All of your endpoints of your intervals, we only use the first and last ones. We use all the other ones with a 2, use them twice. And then we just find the function value at each of those points. F of 0 is 3, f of 1 is 5, and so forth. And then whatever, you guys can type that in a calculator. That's some number. I don't know what the number is. You can find that. I did the same thing on the midpoint rule one. Okay, midpoint rule here. So we're going from 0 to 3. So our delta x is b minus a over n. It's a half. So we have an interval every half. We want the midpoint of each of those intervals. So halfway between 0 and a half is a quarter. Halfway between 0.5 and 1 is 0.75. Halfway between 1 and 1.5 is 125, and so forth. And so our function, or integral, or area, is approximately delta x times the sum of all those function values. And then again, just plug each of these values into that function right there. You can do that. Get all those nasty decimals, add it all up, multiply by a half. Done. Okay, improper integrals must be written as a limit. If you're not writing a limit at every single step until you finally take the limit at the very end, it's completely wrong. That's what I'm testing you on here, is do you know to write the limit? So, because we have this infinity, we need the limit as t goes to infinity from 5 to t. We know the antiderivative 1 over x cubed. We know this is going to converge, by the way, because 3 is bigger than 1. So we get this antiderivative. Then we take the limit. 1 over t squared goes to 0 as t goes to infinity. So the answer is just 1 over 50 is what I got. Okay, same idea here. If we want to try to find this improper integral, we need to take a limit. So the limit, where the infinity was, limit as t goes to infinity of Integral 4 pi to t of cosine x dx. And we get this limit. Sine of t does not converge it to anything as t goes to infinity. This limit diverges. I don't even care what the other one does. It diverges. Sine doesn't converge. Okay, this guy here has an asymptote. That's what that says, asymptote, at 0. So I need to break this up into two separate integrals. The integral up to 0, the left side, and then the right side. Each of those has a limit. And I keep writing limit until I finally take the limit. So when I worked it out, I got -3/2 for the left side and 6 for the right side. So we add those together and I got 9/2. Getting closer. Okay, this one was actually kind of long. I think that, yeah, this is all, it goes all the way down here. This is a really long one. And I got a different answer than Wolfram Alpha did, and I'm not convinced they're right. I looked at their answer two different ways, and they got half the answer I did. But then looking at their indefinite integral, it was right. So this answer may be wrong. It may be half of this, but I couldn't find a mistake. Okay, so first thing we want to notice is if we let u be e to the x, then that thing right there is a u squared. That is e to the x squared. It's just rules of exponents. So that's going to be something like a u over 1 plus u squared, or a du over 1 plus u squared, which is an arctangent. Okay. We also have these infinities, so this is an indefinite integral. We need to split this into two integrals, dividing anywhere we want. I chose to split it at 0. Okay, so I'm doing the indefinite integral first, using this substitution, and I get this. 6 over square root of 6, that's just square root of 6. Arctan of u over root 6. And now I want to do my left hand and my right hand side. So this is the limit as t goes to infinity. That's negative infinity. This is the left side. Okay, when t goes to negative infinity, e to the x goes to negative infinity. Arctangent goes to negative pi over 2. At 0, arctangent of pi over 2 is 0. Okay, and then same thing on the right-hand side. E to the x goes to infinity as t goes to infinity. Arctangent of infinity, or the limit, is pi over 2. So we get a pi over 2 plus or minus a negative pi over 2. So we get a pi times the square root of 6. Again, if you can find a mistake in this and you get Wolfram Alpha had this as their definite integral, but they agreed with this as the indefinite integral. And I can't find an arithmetic mistake anywhere. Maybe I'm just being silly and these two are equal. Somebody check that for me. I don't think they are. Okay, this one, arc length. So the length of a curve, we need a y prime, and then we're going to have to square y prime. So we take the derivative, we get this thing, we square it, and we get this. Then we want the definite integral from our limit 0 to 2, square root of 1 plus f prime squared. And now I'm going to have to clean this up. I can promise you if you get something ugly like this will turn into a perfect square trinomial, which it does. I get a common denominator of 4, and I get this. That's all over square root of 4, which of course is 2. That's where that 1/2 comes from. That 4 I just brought out. That's 2 outside. This is a perfect square trinomial. That's x squared plus 2 squared. Take the square root. And everybody's positive. I don't have to worry about absolute values or anything. Then I do that antiderivative, plug in my limits, Get 10 over 3. We're almost done. This is our last one. Yay. Okay, and then we've got this pressure problem. I really like this problem. So we put our x-axis up at the water level. Our y-axis points straight down. So this is positive y down here. We build this little rectangle down at some level y. That's a little y right there. So it's delta y thick. I just need to figure out how long it is. So I drew a couple of triangles. So I drew this triangle versus the whole triangle. This one is some x. That's this side right here. This distance here is 5, the whole thing, minus y, right there. Okay, over on the big triangle, that's 3.5, half the 7, by 5. Do a little proportion, solve for x, and there's x. But the whole length of that rectangle is double that, so we need a 2 there. So there's the area of that rectangle. So the force on that rectangle is the pressure, delta times y, times the area. Then we just integrate. The limits I'm using for y here are from 0 to 7. So I just do the integral. And I got this, whatever that is. And this is in pounds. We need units here. Okay, I went through, I checked most of these answers. This one I did not check, so you definitely want to check the details here. Same with this arc length problem. I did not check that answer. And the process is right, but you want to check the details. And again, this one, I have looked at it. I spent 20 minutes looking at it, and I am convinced this is right. But if you get something that looks more like this or this over 2, you might be right. Let me know what you did and I didn't do. Okay, good luck on the test.